George. So I'm just going to go ahead and start off by saying that I think everyone in this room that has presentations could go on and talk for an hour or more on these jobs. So to cut it down to 10 minutes is tough, so we're going to have to run through some things pretty quickly. We'll do our best to get through it. So this is just an overall picture of the job looking out over the park. It's called 100 above the park for that reason. So on the west side of the project is the beautiful Forest Park. On the east side, you can look out towards downtown St. Louis, Missouri. So it's a pretty picturesque view from pretty much any room in the building looking out over that park. I want to go ahead and thank a bunch of the team that worked on the job. MKA was our structural engineer out of Washington. Our architect was Studio Gang Architects out of Chicago. Clayco was a general contractor. Concrete Strategies, who again is my employer, I'm a project manager for Concrete Strategies. We did all of the turnkey construction, concrete construction work on the project. Ventana was a curtain wall contractor. Cisco did all the PT design and supply. They're also based out of Chicago. And then Ready Mix was supplied by Kienstra Materials. So one thing I'm going to kind of talk about today is more related to the concrete construction of the job. I think playing a short video shows you the constructability of it. We're all here at a concrete conference, so what I want to talk about is how we built the building. So this job is a 37-story building, and we built it in about 18 months from foundations to top out of concrete. So we were flipping a floor about a floor a week once we got to the residential tower. So I think talking through that is what I want to highlight today, the floor plan, some of the different rebar and PT constraints we worked through, and then just talk about some of our suppliers and formwork and equipment we use to make this project successful. So I kind of highlighted these things we're going to talk about, and then last we'll get into the overall construction cycle if we have time to talk through that. So the footprint of the building is a 25,000 square foot footprint. The slab on grade was a structural slab on grade, which was just mildly reinforced, so there was no post-tension cable in the slab on grade. As we went elevated, the parking garage was a 25,000 square foot footprint, and we poured it in two different pours, each one about 12,500 square feet. We were able to flip the parking garage in about 7 working days per pour. Level 7 was a big transfer level where we had a big pool and amenity deck. We had deep transfer beams that we'll touch on a little bit later. But what I want to highlight is the residential tower. So each tower footprint was built using 4 level tiers. So each tier was growing, and you can see that in some of the later pictures. Each tier got bigger as we went up. So the footprint grew from around 11,000 square feet of floor to about 13,000 square feet of floor. The 4th floor in every tier had a balcony level. So one of the big design constraints was how do we waterproof this balcony level? How do we have a seamless transition from the inside space to the outside space while waterproofing that balcony level? And then the structural elements associated with each floor, we had 16 wallums, as I call them. We had 3 typical columns, 1 elevator core, and 1 shear wall on the south side. The geometry of the building gave us some struggles with the layout. Your layout almost had to be 100% total station driven. So one thing we did in-house with our in-house design team was come up with a slab edge plan that took into account the curtain wall versus the metal stud paneling. So a notch inward that you can kind of see where we showed the embeds, that the slab edge is notched inward and then bumps out for the metal studs as the curtain wall ran past each floor and the studs ran from top of slab to underside of slab, so that's something to anchor to. So this picture does a good job on the north side showing you those slab notches. So you can kind of see that notch there where the curtain wall passes and where the studs continue from slab to slab. And you can kind of see that in the pictures, below in the picture as well, where we transition from curtain wall to metal studs. The wallums, as I call them, is kind of a made-up term, but it's more or less as a column, but we treated it almost like a wall. What I want to highlight is at the bottom of every tier, that column starts out at 4 feet tall, or 4 feet wide, 4 feet wide. And at the top of that tier, that column is 9'10" wide. So to set a column form that 1 tapers and slopes, and 2 is big enough to encompass a growing column was something we had a challenge with. What we ended up doing on the job was just make simple studded panels. It seems so simple to say it, but it truly is just 3/4 inch plywood with 2x4 studs, and then 2x6 whalers and taper ties. The rebar you can see in the picture is pretty cool to see setting that rebar to the slope. So it took a lot of time to plan and work with our rod busters of what that shape was going to be and to make sure they had adjustment in those ties. So we pretty much relied on a lap of all the column ties. That way they could set that slope exactly what we needed it to be. This picture, what I want to highlight here is truly those wall lums we're talking about. So you can see in that picture, the back side of that column is perfectly straight and plumb, and that front side is sloping as the building's growing. So again, to highlight it, that floor is growing from a 4-foot wide column to a 9'10" wide column. So the entire footprint is growing by about 5 feet over those 4 floors. In the essence of time, we're going to kind of sprint through rebar, but the one thing I want to highlight the most is the level 7 transfer beam. So one thing we did as part of our schedule to try to increase schedule, because that's what's most important these days, is we brought the elevator core up ahead of time. We put large blockouts in the elevator core to allow the transfer beams to tie into. So in-house, we did some modeling of that rebar to see how congested it was going to be to plan with those blockouts in the elevator walls. This is a picture looking in the northeast corner of the elevator core. That transfer beam was 7 feet deep and 5 feet wide. On bottom, we had 48 number 14 bars stacked in 4 layers and 36 number 11 bars in the top, stacked in 3 layers. But we had to intertwine all those bars amongst the column rebar in the wall and the wall verticals and horizontals in the wall with concrete above and below, so you had no play in those verticals. So trying to plan all that and make it work was a just job in and of itself. Here's another view just looking down the beam. Again, 7 feet deep, 5 feet wide. I think we had stirrups like 5 inches on center on this specific beam. Post-tension cable design, again, provided by Cisco, who's based out of Chicago. So they did all the PT design and all the PT supply. One thing that's interesting on this job is when I think of post-tension cables, we like to think of like straight runs, nice square forms, easy to stress out of. This overview kind of shows you the curvature of all the cables and how we had to make them work. So everything's arching, sweeping. We had a lot of backup bar, a lot of hairpins to prevent blowouts on this job. But what Cisco was able to provide was called angled PT pocket formers, or the angled PT cones. So it took a little trial and error, but they were able to supply us with 30-degree and 45-degree pocket formers. So when we had an angled edge form, that cone would sit square on the form despite the edge form being on an angle. This is a picture just looking down on the deck from up on top of the elevator core. Again, just highlighting the angles and the sweeping of the cables. This is a day or so before the deck pour, so we're not 100% ready, but you at least can see all the work in place of the PT cables. Concrete we'll touch on briefly. Historically, we all think of concrete as 4 components, right? Sand, water, cement, and rock. Today, with all the chemical admixtures, it's a science that's changing the landscape. Our supplier, Kienstra, was pretty paramount in the pre-planning side of things, and they supplied 2 mixes I want to highlight on this project. So there was a 10,000 PSI self-consolidating mix that was a 27 to 30 inch spread. That mix had a 56-day spec at 10,000 PSI. We were breaking around 10,000 PSI at 14 days. The 6,000 PSI deck mix was a 3,000 PSI requirement to stress. We wanted to stress the next day to turn our cycle. So we had to have something that was workable enough to get up 37 stories up a stack pipe, but set quick enough to be able to set and allow us to stress cables the next day. We're going to breeze through some form work. So what I want to highlight here is you can see the center elevator core. You can see all the deck form work. All of the deck form work was provided by Perry Formworks. We had perimeter tables in the tower and some perimeter tables on the west side in the garage. 90% of the garage formwork was hand set framing. We set the towers, laying out the joists and laying plywood. This is a single seat picker to fly a perimeter table. So we had 2 different seat pickers on the job. A single seat picker flew the single tables, and a double seat picker was custom built by Perry to allow us to fly some of these larger tables with the awkward, obtuse angles and shapes. We had a Vario shear wall from Perry, which allowed us to anchor it to the wall ahead of time, so the wall form was up in place prior to the day of the pour. Here's just a picture from the south side, kind of highlighting all the different elements of the formwork. The FCO self-climbing core, there's 2 things I want to highlight about it. One is it has 4 hydraulic cylinders on the inside of the core. Those hydraulic cylinders allow it to lift and jump itself without the use of a crane. We were able to jump it 9'8", which was our pour height, in 9 minutes and 37 seconds, which is pretty remarkable. We could have flipped this core on probably a 3-day cycle, but based on schedule and logistics, we had to flip it once a week to stay in line with our placing boom on the deck. The placing boom was a 36-meter placing boom, which is about the largest you can get on the market. Again, we had to try to battle it with, it has to reach the south end of the deck, but also get up and over the core to place the north side of the deck while we're pouring the deck placement. And then again, just to highlight the schedule very quickly here, as I know we got to get to everybody else. Day 1, we would pour the slab and the vertical on the south side. Day 2, we'd stress. Day 3, we're flying formwork. Day 4, we're finishing formwork. Day 5 and 6, we're doing rebar. To highlight that, on the south side, everything highlighted in blue, so that south shear wall and the corresponding columns, we poured those the same day the deck was poured. So it could be the hot summer months in St. Louis, and we were putting NCA in the first 100 yards of concrete to make sure we could get on it that day to pour the walls and columns. Because if we didn't get those poured the same day, the cycle was broken. So on day 2, we finished the rest of the vertical when we're stressing cables. Day 3, we're flying formwork. Day 4, we're finishing formwork. Day 5 and 6, we're pouring the core and then moving on to the next level. So this is just one last photo showing the kind of all the work in progress, the curtain wall glass, the concrete structure, all the tapered shapes, the elevator core, kind of all in one good photo. So that's kind of where I'll end it. And if we got time for questions, great. If not, I'll be around afterwards.